Hello, Physics 2 people. Um, Welcome back. This is a video describing the macroscopic picture of magnetic properties of matter. So we've learned what magnetic fields do to electric charges, and then we've learned how electric charges when they move, can create magnetic fields. Um, but that's all been about individual point charges. Um, as when we had electric fields, we find that you can kind of average over all the little atomic variations and come up with a description of the uh, effect that matter has on magnetic fields. So just a reminder for electric fields, so this is just a reminder. For electric fields, we had dielectric materials. And the die in that case doesn't mean that you want to die. It means that um, they oppose. They oppose the external electric field. So if you start with an electric field and then in space, and then you fill the region with dielectric material, the resulting combined electric field will actually be smaller than it was before. And for linear homogeneous materials, so it means they're the same in all directions, and basically the amount of polarization is proportional to the external field. Um, so for linear materials, we had that you could simply account for this dielectric phenomenon by replacing epsilon naught, the permittivity of free space, with epsilon, the permittivity of the material. And the permittivity of the material can be written as a dielectric constant times the vacuum value. And then sometimes it's also written as 1 minus or 1 plus chi e. So that would be times epsilon naught. So the dielectric constant equaled 1 plus chi, and chi is called the dielectric susceptibility, or the electric susceptibility of the material. So these are just ways to account for the material by saying that overall, all they do is kind of stretch or rescale the electric field. And so you can account for that by just rescaling the dielectric constant. In other materials, nonlinear materials or non-homogeneous materials, things like some crystals treat one direction very differently than another. This probably is not a good enough description. You'd have to go into more details. But for us, this works. We're going to more or less do the same thing for magnetic fields. However, magnetic materials are a little more complicated. There's more variety for magnetic materials. And in magnetic materials, there are three basic categories. So kind of category one are called diamagnetic. Okay, so diamagnetic materials are materials which, in general, weakly oppose the ambient magnetic field. They tend to reduce the magnetic field. This is typically a weak effect. When studying the electric structure of what makes something a diamagnetic material, it turns out these are materials where um, the um, intrinsic atomic magnetic moments vanish. So, for those of you who've had chemistry, this is you have different shaped orbitals, and those orbitals represent electron clouds in some sense, and so you shouldn't be surprised that there's some correlation between the electrical current flowing around an atom and the various orbital shapes. And it turns out that for some materials, there is no um, intrinsic um, uh, swirl or current, and therefore no intrinsic magnetic moment associated with the atom. And these materials all become diamagnetic materials. Case two is when there is some intrinsic magnetic moment on each atom. So if each atom has an intrinsic magnetic moment, it's kind of like, just even regardless of whatever else is in the problem, that's like having a little loop of current. And then if you were to put an external magnetic field, well, each atom with its loop of current is kind of like a little magnet. And if you have a bunch of magnets in the presence of another magnet, they all want to stack up together. And so they kind of enhance the effect. So this gives in this case, it's called paramagnetism. And this is a weak enhancement of the magnetic field. There's a third case, which is called ferromagnetism. Ferrous refers to iron, so these are materials like iron. And these have an anomalously large, these have huge magnetic responses. Um, so, we're thinking of magnetic, or sorry, we're thinking about these as like an enhancement of something like a factor of 100 enhancement from the external ambient magnetic field. Um, okay. These kind of materials tend to have, well, the atoms actually group into clusters called domains, and the magnetic interactions are so strong that they extend far beyond individual atoms, and you get these domains which act as like little separate magnets all together. And if they are in the presence of an external magnetic field, then all the domains can align, and that's when you have magnetized, say, a piece of iron. Yeah, okay, there. Lots of detail here on the atomic relationship between atomic and macroscopic numbers, but we're going to skip over that. So, like with dielectrics, we can define um, magnetic constants. And susceptibilities. So really, as long as it's a linear homogeneous material, we just call them linear materials. You can really just work the problem out for vacuum, where you get mu naught, and then you can simply replace mu naught with mu. So this is mu naught is the permeability of free space. Mu is be the permeability of the material, and it simply equals a constant k. So it's the magnetic constant times mu naught. Or just like with electric fields, you could write k in terms of a susceptibility or a deviation away from 1 plus chi m times mu naught. And just what's different, so this is very similar to electric fields, but it's a little different because here we have both kinds of responses. So if chi is small and negative, that corresponds to diamagnetic. If chi is small and positive, this is paramagnetic. And if chi is huge, roughly 100, then this would be ferromagnetic. When you calculate this for ferromagnetism, you actually, when you kind of at first cut, you actually get a diverging result, which you have to interpret as meaning huge, not really infinite. All right. In practice, just remember you can ignore this effect, calculate things as if it was free space, and then just fill in the appropriate value for the constant. There is one other kind of curious or interesting effect, And that is that because K is about the same as chi, which is like, a factor of 100 for ferromagnetic materials. What we find is field lines would rather follow the metal rather than leak into the air. So um, that means that if I had a magnet sitting there, and it would create field lines which look unusual sort of dipole pattern. On the other hand, if I had a weird piece of metal and I were to put the magnet next to that piece of metal, rather than forming a nice dipole pattern, those field lines would go out and would prefer to follow the metal around rather than leak into the air. The effect there, the enhancement is so much larger inside the material that they will follow the metal no matter where it bends. I think we've all seen this effect. So if I have a table and I have some paper clips here, and I hold a magnet way up here, the paper clips don't really respond if there's enough of a gap. On the other hand, if you make a chain of paper clips, one touching another, they can then paper clips along the table will be attracted to it. So this is a situation where if you didn't have the metal there in the form of other paper clips, the magnetic field lines would just fill out through the air and would be so weak when it reached the table, you wouldn't be able to move this paper clip. On the other hand, because the metal provides the magnetic field lines a path where they can stay wholly within the metal, they will take that path. So every line that starts out up here finds its way down to this paper clip, and you're actually able to drag this paper clip around. That's kind of an interesting effect. All right, so that's going to be what we need for a kind of macroscopic view of magnetic material interactions. There's a lot more to it. You probably could hear me shuffling around with my notes, but a lot of that gets into you can relate orbital, if you model atoms with little planetary models with electrons orbiting the nuclei, you can relate, at least classically, the magnetic material response to the details of the orbital motion of the atoms. And while that's important, especially if you go on and take modern physics, I think whenever you need that material, the instructor would review it for you. So I'm not going to go over it here. So that's all I want to cover for this video. In the next one, I want to talk about inductance. I want to define it and calculate it in a few simple examples, and we may do that over a couple videos, in fact. But we will, over the next couple of videos, we'll go through inductance, look at mutual inductance, look at self-inductance, how to calculate it for some simple geometries, and then we will also talk about transformers. All right, so let's see you next time.